Since the first humans looked upward and witnessed the sun vanishing in the middle of the day, eclipses have been woven into the deepest fabric of human consciousness, inspiring myths of dragons devouring the sun, prompting ancient astronomers to develop mathematics sophisticated enough to predict these celestial events centuries in advance, and eventually becoming the very tool that proved Einstein's revolutionary theory of general relativity, forever changing our understanding of space, time, and gravity itself. Let yourself settle in now, finding that comfortable position where your body can truly relax. Perhaps you're lying in bed, the soft weight of blankets around you, or maybe you're resting somewhere quiet where the world feels far away. Wherever you are, know that you're about to embark on a gentle journey through one of the most magnificent phenomena our universe has to offer. We're going to travel together through thousands of years of human history, across continents and cultures, from ancient Babylon to modern observatories, all while exploring the beautiful, celestial dance that creates these moments of cosmic wonder. There's something profoundly peaceful about eclipses when you truly understand them. They remind us that we live on a small spinning world, orbiting a medium-sized star, accompanied by a faithful moon that has been our companion for over 4 billion years. The shadows they cast upon our world are gentle reminders of our place in this vast cosmic arrangement, and tonight we'll explore every facet of these remarkable events together. So take a slow, deep breath. Let your shoulders drop, let the tension in your jaw soften, and let's begin our journey into the shadows. The story of eclipses is in many ways the story of humanity itself. Long before written language, before agriculture, before the first cities rose from river valleys, our ancestors watched the sky with wonder and sometimes with fear. The sun was life itself, the great fire that brought warmth and light, that made plants grow and kept the darkness at bay. So when that sun began to disappear in the middle of a clear day, when an invisible force seemed to consume the source of all life, the experience must have been utterly terrifying. Imagine yourself standing on an open plain, perhaps 15,000 years ago. You know nothing of orbital mechanics or celestial bodies. You know only that the sun rises each morning and sets each evening, as reliable as your own heartbeat. And then one day, without warning, a darkness begins to creep across the sun's face. The air grows cold. Birds stop singing and return to their roosts, confused by this sudden twilight. The world takes on an eerie quality, shadows sharpening in strange ways, the light becoming something you've never seen before. And then for a few minutes that must feel like eternity, the sun vanishes entirely, replaced by a black disk surrounded by ghostly white streamers of light. This experience, repeated countless times across human history, gave birth to some of our oldest and most enduring myths. In ancient China, people believed a great celestial dragon was attempting to devour the sun, and they would rush outside, banging drums and pots, shooting arrows into the sky, doing everything possible to frighten the dragon away. And of course it always worked, because the sun always returned. In Hindu mythology, the demon Rahu was beheaded by the god Vishnu, but not before Rahu had taken a sip of the nectar of immortality. His immortal head continues to chase the sun and moon across the sky, occasionally catching and swallowing them, though they soon emerge from his severed neck. The Vikings told of two great wolves, Skirl and Hati, forever pursuing the sun and moon across the heavens. During an eclipse, one of these wolves had finally caught its prey, and the people would make as much noise as possible to force the wolf to release its celestial quarry. In Vietnam, the eclipse was caused by a giant frog swallowing the sun or moon. In parts of Africa, it was believed that the sun and moon were fighting during an eclipse, and people would try to encourage them to stop and make peace. These myths, as varied as the cultures that created them, share common threads that tell us something profound about the human experience of eclipses. There is almost always a creature or force consuming the sun or moon. There is almost always fear, followed by relief when the celestial body returns. And there is almost always an element of human participation, a belief that people could influence the outcome through noise, prayer, or ritual. This tells us that our ancestors, while lacking our scientific understanding, were not passive observers of these events. They engaged with eclipses actively, incorporating them into their spiritual and social lives in meaningful ways. But not all ancient peoples viewed eclipses purely through the lens of mythology. Some of the earliest astronomers in human history began to notice patterns in these events, and their observations would lay the groundwork for all of astronomy to come. In ancient Mesopotamia, in the fertile lands between the Tigris and Euphrates rivers, the Babylonian astronomers developed a remarkably sophisticated understanding of eclipses. These scholars, who served in the temples and courts of Babylonian kings, kept meticulous records of celestial events on clay tablets, many of which survive to this day. They observed that eclipses didn't happen randomly, but followed patterns that could, with enough data and careful analysis, be predicted in advance. The Babylonians discovered what we now call the Saros cycle, a period of approximately 18 years, 11 days, and 8 hours, after which eclipses repeat in similar patterns. They didn't understand why this cycle existed, as that would have required knowledge of orbital mechanics that wouldn't be developed for another 2,000 years, but they recognized the pattern through careful observation and record-keeping spanning centuries. This was science in its purest form, observing nature, recording data, finding patterns, and making predictions. One of the most famous Babylonian eclipse records comes from a tablet dating to 763 BCE, which records a total solar eclipse that occurred on June 15th of that year. This eclipse is mentioned in Assyrian historical records as well, making it one of the earliest precisely dated events in human history. The Babylonians noted that this eclipse occurred during a time of civil unrest, and like many ancient peoples, they believed celestial events carried messages about earthly affairs. The Babylonian astronomers developed a system of eclipse prediction that allowed them to forecast lunar eclipses with considerable accuracy. Solar eclipses were more difficult to predict because they are only visible from specific locations on Earth, but the Babylonians could at least predict when a solar eclipse was possible, even if they couldn't be certain it would be visible from their location. This predictive ability gave the astronomer priests considerable power and prestige, as they appeared to have knowledge of the gods' intentions. Meanwhile, in ancient China, astronomers were developing their own sophisticated understanding of eclipses. Chinese records of eclipses date back over 4,000 years, making them among the oldest astronomical records in existence. The Chinese astronomers, like their Babylonian counterparts, served the imperial court, and their ability to predict eclipses was considered essential to the emperor's mandate to rule. According to Chinese tradition, the emperor was the son of heaven, and celestial events were direct communications from the heavens about the emperor's performance. An eclipse could be interpreted as a warning or sign of displeasure, so predicting eclipses accurately was a matter of state importance. Legend tells of two court astronomers, Shi and Ho, who were executed around 2100 BCE for failing to predict a solar eclipse. Though this story may be more myth than history, the Chinese developed their own methods for predicting eclipses, and their records provide invaluable data for modern astronomers studying long-term patterns in Earth's rotation and the Moon's orbit. By comparing ancient eclipse records with modern calculations, scientists can determine how Earth's rotation has changed over thousands of years, a testament to the accuracy and value of these ancient observations. In ancient Greece, eclipses played a crucial role in the development of natural philosophy and early science. The Greek philosopher Thales of Miletus, who lived in the 6th century BCE, is credited with predicting a solar eclipse that occurred on May 28, 585 BCE. This eclipse reportedly occurred during a battle between the Lydians and the Medes, and both armies were so frightened by the sudden darkness that they immediately made peace. While historians debate whether Thales actually predicted this eclipse or whether the story was embellished later, it represents an important moment in intellectual history. The idea that natural events could be predicted through reason and observation rather than attributed solely to the whims of gods. The Greek philosopher Anaxagoras, who lived in the 5th century BCE, correctly proposed that eclipses were caused by the moon passing in front of the sun or into Earth's shadow. This was a remarkable insight for its time, requiring an understanding that the sun, moon, and Earth were physical bodies in space rather than divine entities. Anaxagoras was reportedly charged with impiety for suggesting that the sun was a hot rock rather than a god, showing how revolutionary these ideas were. The Greek astronomer Hipparchus, working in the 2nd century BCE, used eclipse observations to make remarkably accurate calculations of the moon's distance from Earth. By carefully timing lunar eclipses from different locations and applying geometry, Hipparchus determined that the moon was approximately 60 Earth radii away, a figure very close to the modern value of about 60.3 Earth radii. This was one of the first accurate measurements of a celestial distance, achieved through clever observation and mathematical reasoning. The ancient Egyptians, too, observed and recorded eclipses, though their records are less extensive than those of the Babylonians or Chinese. The Egyptians associated the sun with the god Ra, who sailed across the sky each day in his solar barking. An eclipse might have been interpreted as an attack on Ra by the serpent Apophis, the embodiment of chaos, who eternally threatened to swallow the sun and plunge the world into darkness. In the Americas, the Maya developed one of the most sophisticated astronomical systems of the ancient world. The Dresden Codex, one of the few surviving Maya books, contains detailed eclipse tables that allowed Maya astronomers to predict eclipses with remarkable accuracy. The Maya understood the Saros cycle and could predict both solar and lunar eclipses centuries in advance. For the Maya, eclipses were times of danger when malevolent forces threatened the cosmic order, and elaborate rituals were performed to ensure the sun and moon's safe return. As we move through these ancient civilizations, a pattern emerges. Everywhere humans looked up at the sky, they noticed eclipses and tried to understand them. Some developed mythological explanations involving gods, demons, and cosmic creatures. Others began to notice patterns and develop predictive methods. But all of them recognized that eclipses were significant events worthy of attention, record-keeping, and contemplation. This universal human fascination with eclipses speaks to something deep in our nature. We are pattern-seeking creatures, and the sudden disruption of the most reliable pattern in our lives, the daily rising and setting of the sun, demands explanation. Whether that explanation takes the form of a dragon eating the sun, or a mathematical formula predicting orbital alignments, it represents humanity's eternal quest to understand the universe we inhabit. Now, let yourself sink a little deeper into relaxation as we shift our focus from ancient observations to the beautiful mechanics that make eclipses possible. Understanding how eclipses work doesn't diminish their wonder. Rather, it reveals an even deeper beauty in the precise cosmic choreography that creates these events. At the heart of every eclipse is a dance between three celestial bodies: the sun, the moon, and our Earth. Each of these bodies moves through space in its own orbit, and eclipses occur when these orbits align in just the right way. To understand this alignment, we need to consider each body and its motion. Our Sun is a star, a massive ball of hydrogen and helium undergoing nuclear fusion at its core. It contains about 99.8% of all the mass in our solar system, and its gravitational pull keeps all the planets, including Earth, in orbit around it. The Sun is enormous, about 109 times the diameter of Earth, and it lies approximately 93 million miles or 150 million kilometers away from us. This distance is so vast that light from the Sun takes about 8 minutes and 20 seconds to reach Earth. Earth orbits the Sun once per year, travelling along an elliptical path that brings us slightly closer to the Sun in January and slightly farther away in July. This orbit defines our year and our seasons, though the seasons are caused by the tilt of Earth's axis rather than our distance from the Sun. As Earth orbits the Sun, it also rotates on its axis once every 24 hours, giving us our days and nights. The Moon is Earth's only natural satellite, a rocky body about 1/4 the diameter of Earth. It orbits our planet at an average distance of about 239,000 miles, or 384,000 kilometers, completing one orbit approximately every 27.3 days. This orbital period is called the sidereal month. However, because Earth is also moving around the Sun, it takes about 29.5 days for the Moon to return to the same phase as seen from Earth, such as from one full moon to the next. This longer period is called the synodic month, and it's the basis for our calendar months. Now here's where the magic of eclipses begins to reveal itself. The Moon's orbit around Earth is tilted about 5 degrees relative to Earth's orbit around the Sun. This might not sound like much, but it has profound consequences. Because of this tilt, the Moon usually passes either above or below the Sun, as seen from Earth when it's at the new moon phase, and it usually passes above or below Earth's shadow when it's at the full moon phase. If the Moon's orbit weren't tilted, we would have a solar eclipse every new moon and a lunar eclipse every full moon, which would mean an eclipse of some kind roughly every 2 weeks. Instead, eclipses can only occur when the Moon is near one of the 2 points where its orbit crosses the plane of Earth's orbit around the Sun. These crossing points are called nodes, and the line connecting them is called the line of nodes. The line of nodes slowly rotates around Earth, completing one full rotation approximately every 18.6 years. This rotation, combined with the Moon's orbital motion and Earth's motion around the Sun, creates the complex patterns of eclipse occurrence that ancient astronomers worked so hard to understand. For a solar eclipse to occur, the new moon must be near one of its nodes at the same time that the Sun is also near that node, as seen from Earth. When this alignment happens, the Moon passes directly between Earth and the Sun, casting its shadow on Earth's surface. For a lunar eclipse to occur, the full moon must be near one of its nodes, allowing it to pass through Earth's shadow rather than above or below it. The geometry of shadows is essential to understanding eclipses. Any opaque object illuminated by a light source casts 2 types of shadow. The umbra is the darkest part of the shadow, where the light source is completely blocked. The penumbra is a lighter outer shadow, where the light source is only partially blocked. Both the Moon and Earth cast these 2-part shadows into space. During a solar eclipse, the Moon's shadow falls on Earth. The Moon's umbra is a cone-shaped shadow that tapers to a point. At the Moon's average distance from Earth, this umbral cone just barely reaches Earth's surface, creating a small spot of total shadow no more than about 170 miles or 270 kilometers wide. Within this small spot, observers see a total solar eclipse, with the Sun completely blocked by the Moon. The Moon's penumbra is much larger, covering a region thousands of miles wide, where observers see a partial solar eclipse with only part of the Sun blocked. Here is one of the most remarkable coincidences in our solar system, something that makes total solar eclipses on Earth uniquely spectacular. The Sun is about 400 times larger than the Moon, but it's also about 400 times farther away. This means that the Sun and Moon appear almost exactly the same size in Earth's sky, each covering about half a degree of arc. This near-perfect match in apparent size allows the Moon to just barely cover the Sun during a total solar eclipse, revealing the Sun's outer atmosphere, the corona, as a ghostly halo around the black disk of the Moon. This coincidence is not permanent. The Moon is slowly moving away from Earth at a rate of about 1.5 inches, or about 3.8 centimeters, per year. Hundreds of millions of years ago, the Moon was closer and appeared larger in the sky, making total solar eclipses more common and longer lasting. Hundreds of millions of years in the future, the Moon will be too far away to completely cover the Sun, and total solar eclipses will no longer be possible. We live in a special time in Earth's history when total solar eclipses occur, and this is a gift we should appreciate. The duration of a total solar eclipse depends on several factors: how close the Moon is to Earth in its elliptical orbit, how close Earth is to the Sun, and how close the observer is to the centre of the Moon's shadow. The maximum possible duration of totality is about 7.5 minutes, but most total eclipses are much shorter. The Moon's shadow races across Earth's surface at speeds of over 1,000 miles per hour, so even a long eclipse passes quickly for any given location. During a lunar eclipse, the geometry is reversed. Earth's shadow falls on the Moon, and anyone on the night side of Earth can see the eclipse. Earth's umbra at the Moon's distance is much larger than the Moon itself, about 2.6 times the Moon's diameter, so the Moon can be entirely engulfed in Earth's shadow for over an hour during a total lunar eclipse. Lunar eclipses are more commonly observed than solar eclipses, not because they happen more often, but because they're visible from anywhere on Earth's night side. A total solar eclipse is only visible from within the narrow path of the Moon's umbra, which covers less than 1% of Earth's surface. A total lunar eclipse, by contrast, can be seen by anyone who can see the Moon that night, which is roughly half of Earth's population. The colours of a lunar eclipse are particularly beautiful. Even during a total lunar eclipse, the Moon doesn't disappear entirely. Instead, it takes on a reddish or coppery colour, which is why total lunar eclipses are sometimes called blood moons. This colour comes from Earth's atmosphere. As sunlight passes through our atmosphere, it's bent or refracted around Earth and into the shadow cone. The atmosphere scatters away the blue light, just as it does during a sunset, allowing mainly red light to reach the Moon. The exact colour of an eclipsed Moon depends on conditions in Earth's atmosphere. Volcanic eruptions can make the Moon appear darker and redder, while a clear atmosphere produces a brighter, more orange eclipse. Let your mind rest with these images for a moment. Picture the elegant geometry of Sun, Moon and Earth aligned in space. Imagine the cone of the Moon's shadow stretching through the void to touch Earth's surface, or Earth's great shadow reaching out to embrace the Moon in ruddy darkness. These are real physical phenomena happening in the vast spaces around us, governed by the same laws of physics that keep your feet on the ground and make water flow downhill. There's a deep comfort in understanding these mechanics. Eclipses are not random or chaotic events. They follow precise mathematical rules that allow us to predict them centuries in advance. The same eclipse that frightened ancient peoples into believing dragons were attacking the Sun can now be calculated to the second, its path across Earth mapped to the mile. This predictability is a testament to the orderly nature of the universe and to human ingenuity in uncovering that order. Now let us turn our attention more specifically to solar eclipses, those dramatic events when the Moon passes between Earth and the Sun. Solar eclipses come in several varieties, each with its own character and beauty. A total solar eclipse occurs when the moon completely covers the sun's disk. This can only happen when the moon is relatively close to Earth in its elliptical orbit, making it appear large enough to fully cover the sun. Total solar eclipses are the most spectacular of all eclipse types, offering a view of the sun's corona that is impossible to see at any other time without specialized equipment. The path of totality, the track across Earth's surface where the total eclipse is visible, is typically about 100 miles wide and can stretch for thousands of miles as the moon's shadow races from west to east. Outside this narrow path, observers see only a partial eclipse. Many eclipse enthusiasts travel great distances to position themselves within the path of totality, knowing that a partial eclipse, while interesting, cannot compare to the overwhelming experience of totality. An annular solar eclipse occurs when the moon is near the farthest point in its orbit from Earth, making it appear slightly smaller than the sun. When the moon passes directly in front of the sun during an annular eclipse, it doesn't quite cover the entire solar disk. Instead, a bright ring or annulus of sunlight remains visible around the moon's silhouette. Annular eclipses are beautiful in their own right, but they lack the dramatic darkness and corona visibility of total eclipses because the sun's bright surface is never completely hidden. A hybrid solar eclipse, also called an annular total eclipse, is a rare type that appears as a total eclipse from some locations along its path, and as an annular eclipse from others. This happens when the moon's umbral shadow just barely reaches Earth's surface. Near the middle of the eclipse path, where the shadow touches Earth most directly, observers see a total eclipse. Near the beginning and end of the path, where the shadow barely grazes Earth's curved surface, observers see an annular eclipse. Hybrid eclipses are the rarest type, occurring only a few times per century. A partial solar eclipse occurs when only the moon's penumbral shadow falls on Earth, or when an observer is within the penumbra but outside the umbra during a total or annular eclipse. During a partial eclipse, the moon appears to take a bite out of the sun, covering part but not all of the solar disk. Partial eclipses are much more common than total or annular eclipses for any given location, but they're also much less dramatic. The experience of a total solar eclipse is unlike anything else in nature. Those who have witnessed totality often describe it as a profound, even spiritual experience that transcends mere astronomical observation. Let us walk through the stages of a total solar eclipse as an observer on the ground might experience it. The eclipse begins with first contact, the moment when the moon's disk first touches the sun's edge. At this point, a small notch appears on one side of the sun, as if something has taken a tiny bite out of it. This is the beginning of the partial phase, which typically lasts about an hour to an hour and a half before totality. As the moon gradually covers more of the sun, the changes are subtle at first. The sky remains bright, and without special eclipse glasses or filters, you might not notice anything unusual. But as the coverage increases, the quality of the light begins to change. The sun's light becomes noticeably dimmer, though not in the way of clouds blocking the sun. The light takes on a strange silvery quality that's difficult to describe. Shadows become sharper because the sun's disk is becoming smaller, acting more like a point source of light. When the sun is about 90% covered, the changes become more dramatic. The temperature may drop noticeably, sometimes by 10 degrees or more. The sky takes on an eerie twilight quality, darker than normal daylight, but not like ordinary twilight. Animals begin to behave strangely. Birds may roost, crickets may begin chirping, and flowers may start to close as if night were falling. In the last few minutes before totality, the light changes rapidly. The thin crescent of remaining sunlight casts strange shadows. If you're standing near a light-coloured surface, you may see shadow bands, mysterious rippling bands of light and dark that race across the ground. These bands are caused by the thin crescent of sunlight being refracted by turbulence in Earth's atmosphere, similar to the way light ripples at the bottom of a swimming pool. Just before totality, the phenomenon known as Baily's beads may appear. As the moon's edge approaches complete coverage of the sun, the last rays of sunlight shine through valleys and irregularities on the moon's limb, creating a string of bright beads around the moon's silhouette. These beads were first described by the English astronomer Francis Baily in 1836, though they had certainly been observed before. The final bead of sunlight before totality often appears as a brilliant point of light next to the dark disk of the moon, with the faint beginnings of the corona visible around the rest of the moon's edge. This creates a stunning visual effect called the diamond ring, one of the most photographed moments of any eclipse. And then totality. The last sliver of sunlight disappears and the world is transformed. The sky becomes dark, not the deep black of midnight, but a deep twilight blue. Stars and planets become visible. The horizon in all directions glows with the colours of sunset, because you're standing in the moon's shadow and looking out toward areas still illuminated by the sun. But the most stunning sight is the sun itself, or rather, what the sun has become. Where the brilliant solar disk blazed moments ago, there is now a black circle, the silhouette of the moon, surrounded by the ethereal glow of the solar corona. The corona is the sun's outer atmosphere, a region of extremely hot, tenuous gas that extends millions of miles into space. Normally invisible against the brilliance of the sun's surface, the corona is revealed during totality as a pearly white halo with delicate streamers extending outward. No photograph can truly capture the appearance of the corona during totality. It's a three-dimensional structure of incredible delicacy, with streamers and loops and complex patterns that vary from eclipse to eclipse depending on the sun's magnetic activity. The corona glows with a soft, otherworldly light that seems to pulse and shimmer. Many observers report that the corona appears much larger and more impressive in person than in photographs. During totality, you may also see solar prominences, great arcs of glowing gas extending from the sun's surface. These appear as pink or red features around the edge of the moon's silhouette, and they can be quite large, sometimes extending tens of thousands of miles into space. The duration of totality varies from eclipse to eclipse, from just a few seconds to over 7 minutes. Most total eclipses offer 2 to 3 minutes of totality. This time passes with incredible speed. Observers often report that totality seemed to last only seconds, so overwhelming is the experience. As totality ends, the sequence of events reverses. The diamond ring reappears on the opposite side of the sun. Baily's beads flash briefly, and the first direct sunlight in minutes blazes forth. The corona fades from view almost instantly as the sun's surface begins to reappear. The world brightens rapidly, and within minutes the strange twilight of totality gives way to ordinary daylight. The partial phase continues for another hour or so as the moon gradually moves away from the sun, until finally, at fourth contact, the last edge of the moon leaves the sun's disk, and the eclipse is over. Those who experience totality are often profoundly moved. Many describe it as a life-changing event, a moment of connection with the cosmos that transcends ordinary experience. Some people weep, others stand in stunned silence. Almost everyone who sees a total solar eclipse wants to see another, and many become eclipse chasers, travelling the world to stand in the moon's shadow again and again. The corona revealed during total solar eclipses has been a subject of scientific fascination for centuries. Before the space age, Total eclipses were the only way to study this outer region of the Sun's atmosphere, and they remain valuable for certain types of observations even today. The corona is astonishingly hot, reaching temperatures of 1 to 3 million degrees Celsius, far hotter than the Sun's visible surface, which is only about 5,500 degrees Celsius. This is one of the great mysteries of solar physics. How can the outer atmosphere be so much hotter than the surface below it? It's as if you walked away from a campfire and found that the air got hotter the farther you went. Scientists have proposed various mechanisms involving magnetic fields and wave heating, but the coronal heating problem remains an active area of research. The corona is also the source of the solar wind, a constant stream of charged particles that flows outward from the Sun in all directions. The solar wind interacts with Earth's magnetic field, causing the beautiful aurora displays near the poles and occasionally disrupting satellites and power grids during intense solar storms. Understanding the corona is essential for predicting space weather and protecting our technological infrastructure. During solar eclipses, scientists have made many important discoveries about the corona. They've studied its structure, measured its temperature, and observed how it changes over the Sun's 11-year activity cycle. When the Sun is at solar maximum, with many sunspots and active regions, the corona appears more symmetrical and complex. When the Sun is at solar minimum, the corona often shows long streamers extending from the Sun's equator and shorter, more compact structures near the poles. The red and pink prominences visible during totality are also features of the Sun's outer atmosphere. These are great loops of relatively cool, dense gas suspended above the Sun's surface by magnetic fields. Prominences can persist for days or weeks, gradually changing shape as the magnetic fields that support them evolve. Sometimes prominences erupt, throwing their material out into space in events called coronal mass ejections. When these ejections are directed toward Earth, they can cause geomagnetic storms. Now let us turn our attention to lunar eclipses, those gentler celestial events when Earth's shadow falls upon the moon. While perhaps less dramatic than total solar eclipses, lunar eclipses have their own subtle beauty and have played important roles in human history and science. A lunar eclipse can only occur during a full moon, when the moon is on the opposite side of Earth from the Sun. At this time, if the alignment is right, the moon passes through Earth's shadow. Because Earth's shadow at the moon's distance is much larger than the moon itself, lunar eclipses can last much longer than solar eclipses, with totality sometimes exceeding an hour and 40 minutes. Like solar eclipses, lunar eclipses come in several types. A total lunar eclipse occurs when the entire moon passes through Earth's umbra, the darkest part of the shadow. During totality, the moon takes on its characteristic reddish colour as it's illuminated only by sunlight that has passed through Earth's atmosphere. A partial lunar eclipse occurs when only part of the moon passes through Earth's umbra. During a partial eclipse, you can see Earth's curved shadow creeping across the moon's face, a sight that provided early evidence for Earth's spherical shape. A penumbral lunar eclipse occurs when the moon passes only through Earth's penumbra, the lighter outer shadow. Penumbral eclipses are subtle and difficult to observe. The moon dims slightly, but doesn't take on the dramatic colours of a total eclipse. Many penumbral eclipses pass unnoticed by casual observers. The colour of a totally eclipsed moon varies considerably from one eclipse to another. The Danjon scale, developed by French astronomer André Danjon, rates lunar eclipse darkness on a scale from 0 to 4. At L equals 0, the moon is very dark, almost invisible. At L equals 4, the moon is bright copper red or orange, with the umbra's edge appearing bluish and quite bright. The colour depends primarily on conditions in Earth's atmosphere at the time of the eclipse. Volcanic eruptions can significantly affect lunar eclipse colours. When a major volcano injects ash and sulfur dioxide into the stratosphere, these particles scatter and absorb sunlight, making less red light available to illuminate the eclipsed moon. The lunar eclipses following the 1991 eruption of Mount Pinatubo in the Philippines were notably dark. Conversely, when Earth's atmosphere is relatively clear, lunar eclipses tend to be brighter and more orange. The progression of a total lunar eclipse is gradual and stately compared to the rapid drama of a solar eclipse. The eclipse begins when the moon first touches Earth's penumbra, but this moment is essentially invisible to the eye. Only when the moon begins to enter the umbra, typically about an hour later, does the eclipse become obvious. A dark bite appears on one edge of the moon and slowly grows as the moon moves deeper into the shadow. The colours during the partial phase can be quite beautiful, with the shadowed portion of the moon showing deep reds and browns, while the unshadowed portion remains its normal bright grey. The boundary between shadow and light is not sharp but gradual, reflecting the fuzzy edge of Earth's shadow. When the moon is fully immersed in the umbra, totality begins. The moon doesn't disappear, but glows with that distinctive coppery light. The brightness and colour can change during totality as the moon moves through different parts of the umbra. The shadow is darkest at its centre and lighter near its edges. Totality can last anywhere from a few minutes to over an hour and 40 minutes, depending on how centrally the moon passes through the umbra. After totality, the moon gradually emerges from the umbra, the partial phases reverse, and eventually the moon leaves the penumbra entirely, ending the eclipse. One of the beautiful aspects of lunar eclipses is their accessibility. Unlike solar eclipses, which require you to be in a specific narrow path, a lunar eclipse can be observed by anyone on the night side of Earth. You don't need special equipment or protective eyewear. You can watch from your backyard, a city rooftop, or a remote mountaintop. All you need is a clear sky and a view of the moon. This accessibility has made lunar eclipses important throughout human history. Ancient astronomers could observe them from anywhere, compare notes across great distances, and use them to synchronize calendars and measure time. The predictability of lunar eclipses made them valuable tools for navigation and timekeeping long before mechanical clocks existed. Lunar eclipses also provided early evidence for the shape of Earth. The Greek philosopher Aristotle, writing in the 4th century BCE, noted that Earth's shadow on the moon during a lunar eclipse is always circular, regardless of the angle. The only shape that always casts a circular shadow is a sphere, so Aristotle concluded that Earth must be spherical. This was one of the earliest scientific arguments for Earth's shape, derived from careful observation of a natural phenomenon. The gentle pace of a lunar eclipse makes it perfect for contemplation. You can watch the shadow creep across the moon over the course of hours, perhaps sharing the experience with friends or family, perhaps alone with your thoughts. There's no need to rush, no fleeting moment of totality that demands your complete attention. A lunar eclipse invites you to slow down, to breathe, to appreciate the gradual dance of shadows in the sky above. As you rest now, perhaps you can imagine yourself watching a lunar eclipse on a clear, mild night. The full moon hangs bright in the sky, and slowly, almost imperceptibly at first, a darkness begins to encroach upon its face. You watch as the shadow grows, as the familiar bright disk transforms into something strange and beautiful. The moon glows red, suspended in a field of stars that have emerged now that the moon's usual brilliance is dimmed. You feel connected to all the humans throughout history who have watched this same phenomenon, who have wondered at this same celestial shadow play. Chapter 6. Eclipses in Mythology and Folklore across civilizations. Throughout human history, eclipses have inspired some of our most vivid and enduring myths. Every culture that has looked up at the sky has developed stories to explain these dramatic events, and these stories reveal much about how different peoples understood their relationship to the cosmos. Let us journey now through the mythology of eclipses around the world, exploring the rich tapestry of human imagination that these celestial events have inspired. In ancient China, the most common explanation for solar eclipses involved a celestial dragon attempting to devour the sun. The Chinese word for eclipse, shi, actually means to eat, reflecting this mythological understanding. When an eclipse began, people would rush outside making as much noise as possible, banging drums and pots, setting off firecrackers, and shooting arrows into the sky, all to frighten the dragon and force it to release the sun. This wasn't merely superstition, it was a community response to a perceived crisis. The fact that the sun always returned after these efforts seemed to confirm their effectiveness. Chinese court astronomers were expected to predict eclipses so that the people could be prepared to drive away the dragon. The failure to predict an eclipse was considered a serious dereliction of duty, as it left the sun vulnerable to attack. The dragon myth appears in various forms throughout East Asian cultures. In Korea, the eclipse was caused by fire dogs called bulgi that tried to steal the sun or moon on orders from the king of a dark kingdom. In Vietnam, a giant frog was responsible for swallowing the celestial bodies. These variations share the common theme of a creature consuming the sun or moon and the need for human intervention to restore the natural order. In Hindu mythology, the story of Rahu and Ketu explains both solar and lunar eclipses with a tale of cosmic deception and divine retribution. According to the legend, the gods and demons once cooperated to churn the cosmic ocean and produce Amrita, the nectar of immortality. When the nectar emerged, the demon Svarbhanu disguised himself as a god to receive a portion. The sun god Surya and the moon god Chandra recognized the deception and alerted Vishnu, who used his divine discus to behead Svarbhanu. But the demon had already swallowed some of the nectar, making him immortal. His head became Rahu and his body became Ketu, and both were placed in the sky as shadow planets. Rahu eternally chases the sun and moon to take revenge for their betrayal, and when he catches them, he swallows them, causing an eclipse. But because he has no body, the sun and moon soon emerge from his severed neck. This myth is deeply embedded in Hindu astrology, where Rahu and Ketu are considered important celestial influences. Eclipses are seen as inauspicious times when the malevolent forces of Rahu are ascendant, and many traditional practices involve staying indoors, fasting, and performing purification rituals during eclipses. Pregnant women are often advised to take special precautions, as eclipses are believed to have negative effects on unborn children. The Norse mythology of Scandinavia features the wolves Skuld and Hati, who perpetually chase the sun and moon across the sky. Skuld pursues the sun, while Hati chases the moon. During an eclipse, one of these wolves has finally caught its prey. The Vikings would make noise to frighten the wolf into releasing the celestial body, similar to the Chinese response to the dragon. According to Norse prophecy, at Ragnarök, the twilight of the gods, both Skuld and Hati will finally succeed in devouring their quarry permanently. The sun and moon will be destroyed, plunging the world into darkness before the final battle between gods and giants. Eclipses were thus seen as previews of the end times, temporary victories for the forces of chaos that would one day become permanent. In ancient Egypt, the sun god Ra was the most important deity, and his daily journey across the sky was essential to the cosmic order. The serpent Apophis, embodiment of chaos and darkness, eternally threatened to swallow Ra and end the world. Each night, Ra travelled through the underworld, where he had to battle Apophis to emerge again at dawn. An eclipse might have been interpreted as Apophis temporarily gaining the upper hand in this eternal struggle. The Egyptians also associated eclipses with the Eye of Ra, a powerful feminine aspect of the sun god that could become separated from Ra and needed to be coaxed back. Some scholars believe that certain Egyptian myths about the Eye of Ra wandering away and returning may have been inspired by observations of eclipses. In ancient Mesopotamia, eclipses were seen as omens, messages from the gods about earthly affairs. The Babylonians developed elaborate systems of interpretation, believing that eclipses could portend the death of kings, the fall of cities, or other significant events. Interestingly, the Babylonians developed a practice of substitute kings during eclipse periods. When an eclipse threatened the king, a substitute would be placed on the throne temporarily to absorb any negative effects, while the real king went into hiding. After the danger passed, the substitute was often killed to ensure that any bad fortune attached to him wouldn't affect the realm. The ancient Greeks had various explanations for eclipses, ranging from mythological to proto-scientific. Some Greeks believed that eclipses were signs of divine anger or portents of disaster. The historian Herodotus recorded that a solar eclipse during a battle between the Lydians and the Medes so frightened both armies that they immediately made peace. This eclipse, which occurred on May 28, 585 BCE, is one of the earliest precisely dated events in history. However, Greek philosophers also developed naturalistic explanations for eclipses. Anaxagoras correctly proposed that solar eclipses were caused by the moon blocking the sun, and that lunar eclipses occurred when the moon passed into Earth's shadow. This was a remarkable intellectual achievement, requiring an understanding that the sun, moon, and Earth were physical bodies in space rather than divine entities. In the Americas, indigenous peoples developed their own rich eclipse mythologies. The Inca of South America believed that a lunar eclipse was caused by a jaguar attacking the moon. They would shout and make noise to drive the jaguar away, and they would also shake their spears at the sky and make their dogs bark and howl. The reddish colour of the eclipsed moon was seen as the blood of the wounded moon. The Inca were particularly concerned about solar eclipses, which they interpreted as signs of the sun god Inti's anger. During a solar eclipse, the Inca emperor would fast and withdraw from public life, and the people would make sacrifices to appease Inti and restore his favour. The Maya of Central America had a sophisticated understanding of eclipse cycles and could predict eclipses with remarkable accuracy. Despite this scientific knowledge, they also maintained mythological interpretations. The Maya associated eclipses with death and rebirth, seeing them as times when the boundaries between the living world and the underworld became thin. Eclipses were considered dangerous times when malevolent supernatural beings could more easily affect the human world. The Maya Dresden Codex contains detailed eclipse tables that demonstrate their advanced astronomical knowledge. These tables allowed Maya priests to predict both solar and lunar eclipses for centuries into the future. The Maya understood the Saros cycle and other eclipse periodicities, knowledge that was both practical and sacred. In many Native American traditions, eclipses were explained through stories of celestial beings or animals. The Pomo people of California believed that a bear had gotten into a fight with the sun and taken a bite out of it. The Choctaw people believed that a mischievous black squirrel was gnawing on the sun. Various tribes had traditions of making noise during eclipses to drive away whatever creature was threatening the sun or moon. The Navajo traditionally viewed eclipses as sacred but dangerous times. During an eclipse, people were expected to stay inside, remain quiet, and refrain from eating, drinking, or sleeping. Looking at an eclipse was considered harmful, and pregnant women took special precautions. After the eclipse, purification ceremonies were performed to restore harmony. In Africa, Eclipse mythology varies widely among different cultures. The Bata Maliba people of Togo and Benin believed that solar eclipses were caused by a fight between the sun and moon, and that humans should set aside their own conflicts during this time to encourage the celestial bodies to make peace. The Tiv people of Nigeria believed that the moon covered the sun during an eclipse because the sun was too hot and needed to rest. In some West African traditions, eclipses were associated with witchcraft or the activities of malevolent spirits. People would stay indoors and perform protective rituals until the eclipse passed. In other traditions, eclipses were seen as times of renewal or transformation, when the normal rules of the cosmos were temporarily suspended. The indigenous peoples of Australia also developed eclipse mythology. Some Aboriginal groups believed that solar eclipses occurred when the Sun Woman was hidden by the Moon Man, sometimes interpreted as a conjugal visit between the celestial spouses. Other groups saw eclipses as bad omens, signs that someone had broken sacred laws or that sorcery was being performed. In Polynesia, eclipse myths often involved the moon being swallowed by the sun or vice versa. The Maori of New Zealand believed that the sun and moon were the eyes of the sky father Rangi, and that eclipses occurred when these eyes were temporarily closed or covered. What's remarkable about this global survey of eclipse mythology is how similar themes appear across cultures that had no contact with each other. The idea of a creature eating or attacking the sun or moon appears on every inhabited continent. The practice of making noise to drive away the attacking entity is nearly universal. The belief that eclipses are dangerous times requiring special precautions is found in cultures around the world. These similarities suggest that there's something fundamental about the human experience of eclipses that generates these mythological responses. The sudden darkening of the sun, the reliable source of light and life, naturally evokes fear and the need for explanation. The gradual consumption and restoration of the solar or lunar disk suggests a creature eating and then releasing its prey, and the desire to do something, to participate in the cosmic drama rather than passively observe, leads to the noise-making traditions found worldwide. As scientific understanding of eclipses developed, these mythological explanations gradually gave way to naturalistic ones. But the myths haven't entirely disappeared. Many people around the world still observe traditional eclipse practices, whether out of sincere belief, cultural respect, or simply as a way of connecting with ancestral traditions. And even those who understand the astronomical causes of eclipses often find themselves moved by the experience in ways that feel spiritual or transcendent. Perhaps there's wisdom in both approaches. The scientific understanding of eclipses reveals the beautiful precision of celestial mechanics, the elegant dance of sun, moon, and earth through space. The mythological understanding reminds us that we are meaning-making creatures, that we experience the world not just through measurement and calculation, but through story and symbol. Both perspectives enrich our appreciation of these remarkable events. Chapter 7: Eclipses that Changed History. Throughout recorded history, eclipses have coincided with pivotal moments, sometimes influencing the course of events, and sometimes simply providing memorable markers for significant occasions. The intersection of celestial phenomena and human affairs has created some of history's most fascinating stories. Let us explore some of the eclipses that have left their mark on the human story. One of the earliest historically documented eclipses occurred on May 28, 585 BCE, during a battle between the Lydians and the Medes in what is now Turkey. According to the Greek historian Herodotus, the two armies had been at war for 5 years when, in the midst of battle, day suddenly turned to night. Both armies were so frightened by this omen that they immediately stopped fighting and agreed to make peace. The eclipse, Herodotus tells us, had been predicted by the philosopher Thales of Miletus. This eclipse is significant for several reasons. It's one of the earliest events in history that can be precisely dated because modern astronomers can calculate exactly when this eclipse occurred. It demonstrates that eclipse prediction was possible in the ancient world, at least in general terms, and it shows how powerfully eclipses could affect human behaviour, turning enemies into peacemakers in a single afternoon. Whether Thales actually predicted this eclipse is debated by historians. He may have known that an eclipse was possible during that period based on Babylonian eclipse cycles, without being able to predict the exact date or location. Regardless, the story illustrates the growing recognition in the ancient world that eclipses followed patterns that could be understood and anticipated. In 413 BCE, a lunar eclipse played a crucial role in one of the most significant military disasters in ancient history. The Athenian expedition against Syracuse, part of the Peloponnesian War, had gone badly, and the Athenian general Nicias decided to withdraw his forces. But just as the evacuation was about to begin, a total lunar eclipse occurred on August 27th. Nicias was a deeply superstitious man, and his seers advised him that the eclipse was an omen requiring the army to wait for 27 days before moving. This delay proved fatal. The Syracusans used the time to strengthen their defences and trap the Athenian fleet in the harbour. The subsequent battle was a catastrophe for Athens. The entire expedition was destroyed, with thousands of soldiers killed or captured and sold into slavery. This defeat marked the beginning of the end for Athenian power and changed the course of Greek history. The historian Thucydides, who recorded these events, noted that if Nicias had understood the natural cause of the eclipse, he would not have delayed, and the outcome might have been very different. This story illustrates how scientific ignorance combined with superstition could have devastating consequences. In 585 CE, a solar eclipse occurred during a crucial moment in the history of the Byzantine Empire. The Emperor Justinian was engaged in his ambitious project of reconquering the Western Roman Empire, and his general Belisarius was campaigning in Italy against the Ostrogoths. The eclipse was visible across the Mediterranean world and was recorded by multiple historians. The Byzantine historian Procopius described this eclipse as a portent of the troubles to come, including the devastating plague of Justinian that would soon kill millions and permanently weaken the empire. While the eclipse didn't cause these events, its occurrence at such a pivotal time cemented its place in historical memory as a marker of an era of transformation and tragedy. In 1133 CE, a total solar eclipse crossed England on August 2nd, just days before King Henry I died. The coincidence was noted by contemporary chroniclers, who saw the eclipse as a divine omen, foreshadowing the king's death and the period of civil war that would follow. The Anglo-Saxon Chronicle recorded that the eclipse was so complete that people had to light candles to eat their midday meal. Henry the Fiend's death without a clear male heir led to a period of chaos known as the Anarchy, during which his daughter Matilda and his nephew Stephen fought for the throne. The eclipse became part of the mythology surrounding this troubled time, a celestial sign that the natural order was about to be disrupted. Christopher Columbus famously used his knowledge of an upcoming lunar eclipse to save himself and his crew during his fourth voyage to the Americas in 1504. Stranded in Jamaica with damaged ships and running low on supplies, Columbus faced a hostile local population that had grown tired of providing food to the Spanish. Columbus knew from his almanac that a total lunar eclipse would occur on February 29th, 1504. According to accounts of the event, Columbus told the indigenous leaders that his god was angry with them for not providing food and would show his displeasure by making the moon disappear. When the eclipse began as predicted, the terrified locals begged Columbus to intercede with his god. Columbus retired to his cabin, timing the eclipse with an hourglass, and emerged just before totality ended to announce that his god had forgiven them. The moon reappeared, and the locals resumed providing supplies until rescue ships arrived. This story, while it shows Columbus's clever use of astronomical knowledge, also reveals the unequal power dynamics of colonial encounters. Columbus exploited the indigenous people's unfamiliarity with eclipse prediction to manipulate them. A reminder that scientific knowledge can be used for domination as well as enlightenment. In 1715, the English astronomer Edmund Halley organised a systematic observation of a total solar eclipse that crossed England on May 3rd. Halley, famous for calculating the orbit of the comet that bears his name, distributed maps predicting the path of totality and asked observers throughout England to record their observations. This was one of the first large-scale scientific eclipse expeditions. Halley's predictions were remarkably accurate, and the observations collected helped refine understanding of the moon's orbit. The eclipse also provided an opportunity to study the solar corona, which Halley described in detail. This eclipse marked a transition from viewing eclipses primarily as omens to studying them as scientific phenomena. The solar eclipse of July 18, 1860, was the first to be extensively photographed. Astronomers had been attempting to photograph eclipses since the invention of photography in the 1830s, but the technical challenges were immense. The 1860 eclipse, which crossed Spain, provided the first clear photographs of the solar corona and prominences. These photographs proved that the corona and prominences were real features of the sun, rather than optical illusions or artifacts of Earth's atmosphere, as some scientists had argued. Photography transformed eclipse science by providing permanent, objective records that could be studied long after the event and compared across different eclipses. One of the most historically significant eclipses occurred on May 29, 1919, when a total solar eclipse provided the opportunity to test Albert Einstein's general theory of relativity. We'll explore this eclipse in detail in a later section, but its importance deserves mention here. The confirmation of Einstein's predictions during this eclipse changed our understanding of space, time, and gravity, and made Einstein a worldwide celebrity. The total solar eclipse of June 30, 1973, was notable for the use of the supersonic Concorde aircraft to extend totality. A group of scientists flew in a prototype Concorde along the eclipse path at over twice the speed of sound, keeping pace with the moon's shadow. This allowed them to observe totality for over 70 minutes, far longer than any ground-based observation could achieve. This innovative approach demonstrated how technology could enhance eclipse observation and opened new possibilities for studying the solar corona. The extended observation time allowed scientists to study changes in the corona that would be impossible to detect during a typical few minutes of totality. More recently, the total solar eclipse of August 21, 2017, crossed the continental United States from Oregon to South Carolina, the first total eclipse visible from coast to coast since 1918. This Great American Eclipse was witnessed by millions of people and generated enormous public interest in astronomy. The 2017 eclipse was the most observed and most photographed eclipse in history. Scientists used it to study the corona, test new instruments, and investigate how the sudden darkness affected wildlife and the environment. The eclipse also demonstrated the power of celestial events to bring people together, as millions travelled to the path of totality and shared the experience. These historical eclipses remind us that celestial events don't occur in isolation from human affairs. They intersect with our wars and peace treaties, our scientific discoveries and superstitious fears, our technological achievements and cultural practices. Each eclipse is both a cosmic phenomenon and a human event, shaped by and shaping the societies that observe it. Chapter 8: The Scientific Revolution and Eclipses as Tools of Discovery. The scientific revolution of the 16th and 17th centuries transformed how humans understood the natural world, and eclipses played important roles in this transformation. As astronomers developed new instruments and mathematical methods, eclipses became powerful tools for investigating the cosmos. Let us explore how eclipses contributed to the birth of modern science. Before the scientific revolution, the dominant model of the universe in Europe was the Ptolemaic system, inherited from ancient Greece. In this model, Earth sat motionless at the centre of the universe, with the sun, moon, planets, and stars orbiting around it on crystalline spheres. This geocentric model could predict eclipses reasonably well, which seemed to confirm its validity. Nicolaus Copernicus, a Polish astronomer working in the early 16th century, proposed a radical alternative, the heliocentric model, with the sun at the centre and Earth orbiting around it. Copernicus's model was simpler in some ways than the Ptolemaic system, but it faced significant objections. If Earth was moving, why didn't we feel it? Why didn't objects fly off the spinning planet? And importantly, the Copernican model didn't initially predict planetary positions any better than the Ptolemaic model. Eclipses provided one way to test these competing models. Both systems could predict when eclipses would occur, but they made slightly different predictions about the details. As astronomical observations became more precise, these differences could potentially distinguish between the models. The Danish astronomer Tycho Brahe, working in the late 16th century, made the most accurate pre-telescopic astronomical observations in history. Tycho observed several eclipses and used them to refine his understanding of the moon's orbit. His precise measurements would later be crucial for Johannes Kepler's discovery of the laws of planetary motion. Kepler, working with Tycho's data in the early 17th century, discovered that planets move in elliptical orbits rather than perfect circles, and that they move faster when closer to the sun. These laws of planetary motion applied to the moon as well, and they allowed much more accurate predictions of lunar eclipses. Kepler's work provided strong support for the heliocentric model and laid the foundation for Newton's theory of gravity. The invention of the telescope in 1608 transformed astronomy. When Galileo Galilei turned his telescope to the sky in 1609 and 1610, he made discoveries that challenged the old cosmology. He saw mountains and craters on the moon, revealing it to be a world rather than a perfect celestial sphere. He discovered 4 moons orbiting Jupiter, proving that not everything orbited Earth. He observed the phases of Venus, which could only be explained if Venus orbited the Sun. Telescopes also enhanced eclipse observations. Astronomers could now see details of the solar corona and lunar surface that had been invisible to the naked eye. They could time the contacts of eclipses more precisely and measure the positions of celestial bodies more accurately. Isaac Newton's publication of the Principia in 1687 marked a watershed in the history of science. Newton showed that the same force of gravity that makes an apple fall from a tree also keeps the moon in orbit around Earth, and Earth in orbit around the Sun. His mathematical laws of motion and gravitation could predict the motions of celestial bodies with unprecedented accuracy. Newton's theory allowed astronomers to calculate eclipse predictions with much greater precision than ever before. They could account for the subtle gravitational influences of the Sun, Earth, and Moon on each other, producing eclipse predictions accurate to within minutes. This predictive success was powerful evidence for the validity of Newton's physics. Eclipses also provided tests of Newton's theory. The Moon's orbit is complex, influenced by the gravitational pulls of both Earth and the Sun. Newton himself struggled to fully account for the Moon's motion, and the lunar problem occupied astronomers for over a century. Eclipse observations provided crucial data for refining the mathematical models of the Moon's orbit. Edmund Halley, Newton's friend and the astronomer who financed the publication of the Principia, made important contributions to eclipse science. Halley calculated the orbits of comets and correctly predicted that the comet of 1682 would return in 1758. He also organised systematic eclipse observations and produced detailed maps predicting eclipse paths. Halley recognised that precise timing of eclipses from different locations could be used to determine the size of the solar system. The basic principle was triangulation. By measuring how long an eclipse lasted from different points on Earth, astronomers could calculate the distance to the Moon or Sun. This technique, applied to transits of Venus across the Sun, eventually yielded the first accurate measurements of the astronomical unit, the distance from Earth to the Sun. The 18th and 19th centuries saw eclipse expeditions become major scientific undertakings. Astronomers travelled to remote locations to observe eclipses, bringing increasingly sophisticated instruments. These expeditions were expensive and logistically challenging, but the scientific rewards justified the effort. During the total solar eclipse of 1806, Spanish astronomer José Joaquín de Ferrer made careful observations of the corona and concluded that it was a feature of the Sun rather than the Moon or Earth's atmosphere. This was an important step in understanding the nature of the corona, though debate continued for decades. The development of spectroscopy in the mid-19th century opened new possibilities for eclipse science. Spectroscopy involves spreading light into its component colours and analysing the resulting spectrum. Different elements produce characteristic patterns of bright or dark lines in the spectrum, allowing scientists to determine the chemical composition of distant objects. During the total solar eclipse of August 18, 1868, several astronomers observed the spectrum of the solar prominences. The French astronomer Jules Janssen and the English astronomer Joseph Norman Lockyer independently discovered a bright yellow spectral line that didn't match any known element. Lockyer proposed that this line came from a new element, which he named helium after the Greek word for sun, helios. Helium wasn't isolated on Earth until 1895, 27 years after its discovery in the Sun. This was a remarkable demonstration of the power of spectroscopy and eclipse observation to reveal information about the cosmos that couldn't be obtained any other way. The eclipse of 1868 also allowed Janssen to develop a method for observing solar prominences without an eclipse. He realised that the prominences' spectral lines were bright enough to be seen against the sky if observed through a spectroscope tuned to the right wavelength. This discovery meant that astronomers no longer had to wait for rare total eclipses to study these features of the Sun. Photography became increasingly important for eclipse science in the second half of the 19th century. The first successful photograph of a total solar eclipse was taken in 1851, and by the 1860s, eclipse photography had become routine. Photographs provided permanent records that could be studied at leisure and compared across different eclipses. The American astronomer Samuel Langley used eclipse observations to study the solar corona's temperature. By comparing the brightness of the corona at different distances from the Sun, Langley estimated that the corona was extremely hot, perhaps millions of degrees. This was a puzzling result, since the corona is farther from the Sun's energy-producing core than the visible surface. The coronal heating problem that Langley identified remains an active area of research today. By the late 19th century, eclipse expeditions had become elaborate international efforts. The total solar eclipse of 1870 was observed by expeditions from multiple countries, including teams that travelled to Spain, Algeria, and Sicily. These expeditions brought spectroscopes, cameras, and other instruments, and their observations significantly advanced understanding of the Sun. The 1870 eclipse occurred during the Franco-Prussian War, and the French astronomer Jules Janssen made a dramatic escape from besieged Paris in a balloon to reach the observation site in Algeria. Unfortunately, clouds prevented observation, but Janssen's dedication illustrated the importance scientists attach to eclipse observations. Eclipse expeditions also served as training grounds for astronomers and testing grounds for new instruments and techniques. Young astronomers gained experience in fieldwork and observation, while new technologies were evaluated under the demanding conditions of eclipse observation. Many techniques developed for eclipse work later found applications in other areas of astronomy. The scientific study of eclipses reached a climax with the 1919 expedition to test Einstein's general theory of relativity, which we'll explore in detail in the next section. This eclipse demonstrated that celestial observations could test fundamental theories of physics, not just astronomy. Eclipses had become tools for understanding the deepest nature of space and time. Chapter 9: Einstein, Eddington, and the 1919 eclipse that proved relativity. In the history of science, few moments are as dramatic as the confirmation of Einstein's general theory of relativity during the total solar eclipse of May 29, 1919. This eclipse transformed our understanding of gravity, space, and time, and made Albert Einstein the most famous scientist in the world. Let us explore this remarkable story in detail, for it represents one of the most beautiful intersections of theory and observation in all of science. To understand the significance of the 1919 eclipse, we must first understand what Einstein's theory predicted and why it was so revolutionary. Isaac Newton's theory of gravity, published in 1687, had been spectacularly successful for over 2 centuries. It explained the motions of planets, moons, and comets with remarkable accuracy. It predicted the existence of Neptune before the planet was observed. It seemed to be a complete and final description of gravitational phenomena. But Newton's theory had a philosophical problem that troubled some scientists. It described gravity as a force that acted instantaneously across empty space, with no mechanism to explain how one mass could influence another at a distance. Newton himself was uncomfortable with this action at a distance and wrote that it was inconceivable that gravity could act without some intervening medium. Einstein's special theory of relativity, published in 1905, created another problem for Newtonian gravity. Special relativity showed that nothing, not even information, could travel faster than light. But Newtonian gravity implied that if the Sun suddenly disappeared, Earth would immediately fly off in a straight line, responding instantaneously to the change in gravity. This contradicted the cosmic speed limit established by special relativity. Einstein spent 10 years, from 1905 to 1915, developing a new theory of gravity that was consistent with special relativity. The result was the general theory of relativity, one of the most beautiful and profound theories in all of physics. General relativity describes gravity not as a force, but as a curvature of spacetime. According to Einstein, massive objects like the Sun curve the fabric of spacetime around them, and other objects move along the straightest possible paths through this curved spacetime. What we perceive as gravitational attraction is actually the result of objects following curved paths through curved spacetime. This might sound abstract, but it has concrete testable predictions. One of the most important predictions is that light itself should be affected by gravity. In Newton's theory, light has no mass, so it shouldn't be affected by gravity. But in Einstein's theory, light follows the curvature of space-time, so it should bend when passing near a massive object like the Sun. Einstein calculated that a ray of light passing close to the Sun's edge should be deflected by about 1.75 arcseconds, a tiny angle, but one that was within the capability of early 20th century astronomical instruments to measure. Interestingly, if one tried to calculate light bending using Newtonian physics by treating light as particles with a tiny mass, one would get a deflection of only 0.87 arcseconds, exactly half of Einstein's prediction. This meant that measuring the deflection of starlight by the Sun could distinguish between Newton's and Einstein's theories. The problem was that stars near the Sun are normally invisible, overwhelmed by the Sun's brilliance. The only time stars near the Sun can be observed is during a total solar eclipse, when the Moon blocks the Sun's light and the sky becomes dark enough for stars to appear. Einstein first proposed this test in 1911, before he had completed the general theory. At that time, he calculated a deflection of 0.87 arcseconds, the Newtonian value. German astronomers planned an expedition to observe the total solar eclipse of August 21st, 1914, from Crimea to test this prediction. But World War I broke out just weeks before the eclipse, and the expedition was abandoned. The German astronomers were briefly detained as enemy aliens before being allowed to return home. This was fortunate for Einstein's reputation. By 1915, he had completed the general theory and realized that the correct prediction was 1.75 arcseconds, twice his earlier estimate. If the 1914 expedition had succeeded, it might have measured a deflection inconsistent with Einstein's incomplete theory, potentially discrediting his work before it was finished. The next opportunity came with the total solar eclipse of May 29, 1919. This eclipse was particularly favourable for testing Einstein's prediction because the Sun would be in front of the Hyades star cluster, a group of bright stars that would provide many targets for measuring light deflection. The British astronomer Arthur Stanley Eddington was one of the few scientists outside Germany who understood and appreciated Einstein's theory during the war years. Eddington was also a Quaker and a pacifist, and he saw the confirmation of a German scientist's theory by British astronomers as an opportunity for scientific internationalism to triumph over wartime nationalism. Eddington organised 2 expeditions to observe the 1919 eclipse. One team, led by Eddington himself, travelled to the island of Principe off the west coast of Africa. The other team, led by Andrew Crommelin, went to Sobral in northern Brazil. By sending 2 expeditions to different locations, the astronomers hoped to ensure that at least one would have clear skies. The expeditions faced numerous challenges. The war had only recently ended, and travel was difficult. Equipment had to be transported to remote locations with limited infrastructure. The astronomers had to set up their instruments, calibrate them, and hope for good weather on the day of the eclipse. On the morning of May 29, 1919, both teams prepared their equipment and waited anxiously for the eclipse to begin. The stakes could not have been higher. If Einstein's prediction was confirmed, it would overturn 2 centuries of Newtonian physics and revolutionize our understanding of the universe. If the measurements showed the Newtonian value, or no deflection at all, Einstein's beautiful theory might be discarded as an elegant but incorrect mathematical construction. On Principe, Eddington faced a tense morning. Heavy rain fell throughout the early hours, and clouds obscured the sky. As the partial phases of the eclipse began, the clouds remained stubbornly in place. Eddington later wrote, that he had little hope of success as the critical moment approached. But just before totality, the clouds began to thin. Eddington and his team worked frantically, taking photograph after photograph through the diminishing cloud cover. The conditions were far from ideal. Many of the photographs showed stars too faintly to be useful, their light dimmed by the intervening clouds. But some plates captured enough stars to potentially test Einstein's prediction. Eddington would later recall that the moment he measured the first plate and saw the deflection matching Einstein's value was the greatest moment of his life. In Sobral, Brazil, the Crommelin expedition had better weather, but faced technical difficulties. Their main telescope, an astrographic instrument with a 4-inch lens, produced blurred images due to the heat affecting the mirror. Fortunately, they had brought a backup telescope, a 4-inch instrument borrowed from a solar eclipse expedition, which produced clearer photographs. After the eclipse, both teams faced months of careful analysis. The photographic plates had to be measured with extreme precision, comparing the positions of stars during the eclipse with their normal positions when the sun was elsewhere in the sky. Any errors in measurement, any distortions in the photographic plates, any problems with the telescopes could produce false results. Eddington worked on his Principe plates during the voyage home and in the months that followed. The analysis was painstaking, requiring careful correction for various sources of error. The Sobral team similarly laboured over their photographs, eventually discarding the results from their main telescope due to the image quality problems and relying on the backup instrument. By autumn of 1919, the results were ready to be announced. On November 6, 1919, a joint meeting of the Royal Society and the Royal Astronomical Society was held in London to hear the findings. The room was packed with scientists and journalists, all aware that something momentous was about to be revealed. The Astronomer Royal, Frank Watson Dyson, presented the results. The Principe expedition had measured a deflection of 1.61 arcseconds plus or minus 0.30 arcseconds. The Sobral expedition, using the backup telescope, had measured 1.98 arcseconds plus or minus 0.12 arcseconds. Both results were consistent with Einstein's prediction of 1.75 arcseconds and inconsistent with the Newtonian prediction of 0.87 arcseconds. The physicist J.J. Thomson, discoverer of the electron and president of the Royal Society, declared that this was one of the greatest achievements in human thought. The confirmation of Einstein's theory was front-page news around the world. The Times of London ran the headline, "Revolution in Science, New Theory of the Universe, Newtonian Ideas Overthrown." The New York Times announced, "Lights all askew in the heavens, men of science more or less agog over results of eclipse observations." Almost overnight, Albert Einstein became the most famous scientist in the world. His wild hair and kindly face became iconic images. Reporters besieged him for interviews. His name became synonymous with genius. The quiet patent clerk who had revolutionized physics in 1905 was now a global celebrity. The 1919 eclipse results were not without controversy. Some scientists questioned the accuracy of the measurements and the handling of the data. The Principe results had large uncertainties due to the cloud cover, and the Sobral results relied on a backup telescope after the main instrument failed. Critics suggested that Eddington, who strongly believed in Einstein's theory, might have unconsciously biased the analysis. Subsequent eclipse expeditions confirmed the light-bending prediction with increasing precision. The total solar eclipse of September 21st, 1922, was observed by expeditions to Australia and other locations, and the results again supported Einstein. By the 1960s, radio astronomy techniques allowed measurements of light bending using distant quasars, achieving far greater precision than optical observations. Today, the gravitational deflection of light is confirmed to better than 1 part in 10,000, and it's routinely used in gravitational lensing studies to map the distribution of dark matter in the universe. The 1919 eclipse holds a special place in the history of science, not just for what it proved, but for what it represented. It showed that scientific truth could transcend national boundaries, that a British expedition could confirm a German theory just months after a devastating war between their countries. It demonstrated the power of astronomical observations to test fundamental physics, and it captured the public imagination in a way that few scientific results have before or since. Einstein himself maintained a philosophical calm about the results. When asked what he would have done if the eclipse observations had contradicted his theory, he reportedly replied, "Then I would have felt sorry for the dear Lord. The theory is correct." This confidence came not from arrogance, but from Einstein's deep conviction that the mathematical beauty of general relativity reflected something true about the nature of reality. The confirmation of general relativity opened new vistas in physics and astronomy. Einstein's theory predicted the existence of black holes, regions of spacetime so curved that nothing, not even light, can escape. It predicted gravitational waves, ripples in spacetime produced by accelerating masses. It provided the framework for modern cosmology, the study of the universe as a whole. All of these predictions have since been confirmed, most recently the direct detection of gravitational waves in 2015, exactly 1 century after Einstein completed his theory. The 1919 eclipse reminds us that some of the deepest truths about the universe can be revealed in moments of darkness. When the moon's shadow fell across Principe and Sobral, it allowed human beings to glimpse the curvature of space-time itself, to see light bending around the sun in accordance with equations written by a physicist in Berlin. The shadow of the moon illuminated the structure of the cosmos. Chapter 10. Modern Eclipse Science and Technology. As you continue to relax and let your breathing slow, let us turn our attention to how modern science and technology have transformed our understanding and observation of eclipses. The tools available to today's astronomers would have seemed like magic to the eclipse watchers of previous centuries. Yet the fundamental wonder of these events remains unchanged. The 20th century brought revolutionary advances in eclipse observation. Where earlier astronomers relied on the naked eye, simple telescopes, and photographic plates, modern scientists deploy sophisticated instruments capable of measuring phenomena invisible to previous generations. Spectroscopy, which had already proven its value in the 19th century, became increasingly powerful and precise. Modern spectrographs can analyze the light from the solar corona with extraordinary detail, revealing the temperatures, densities, and motions of the coronal plasma. By studying the spectrum of the corona during eclipses, scientists have mapped the distribution of different elements and measured the speeds of coronal material flowing outward into the solar wind. The development of coronagraphs in the 1930s allowed scientists to create artificial eclipses, blocking the sun's bright disk with an occulting disk inside a telescope. The French astronomer Bernard Liot invented the coronagraph in 1931, and it opened new possibilities for studying the corona without waiting for natural eclipses. However, coronagraphs cannot fully replicate the conditions of a total eclipse. Scattered light in Earth's atmosphere limits what ground-based coronagraphs can see, and even space-based coronagraphs must block a region larger than the sun's disk, hiding the innermost corona that's visible during totality. For this reason, total solar eclipses remain scientifically valuable even in the age of space telescopes and artificial occultation. The few minutes of totality offer views of the inner corona that cannot be obtained any other way. Eclipse expeditions continue to make important contributions to solar physics, studying the fine structure of the corona, the behavior of prominences, and the dynamics of the chromosphere, the thin layer of the sun's atmosphere just above the visible surface. Radio astronomy added a new dimension to eclipse studies in the mid-20th century. Radio waves from the sun and from distant cosmic sources can be used to probe the corona and the solar wind. During eclipses, radio astronomers can study how the corona affects radio signals passing through it, providing information about the corona's density and structure. The space age transformed solar observation dramatically, beginning with early satellites in the 1960s and continuing with increasingly sophisticated spacecraft. Astronomers gained the ability to observe the sun from above Earth's atmosphere. Space-based observatories can see wavelengths of light, such as ultraviolet and X-rays, that are absorbed by our atmosphere and never reach the ground. The Solar and Heliospheric Observatory, known as SOHO, was launched in 1995 and has been observing the sun continuously for nearly 3 decades. SOHO carries coronagraphs that provide constant monitoring of the outer corona, tracking coronal mass ejections and other dynamic phenomena. The spacecraft has observed thousands of comets that passed close to the sun, many discovered by amateur astronomers examining SOHO images. The Solar Dynamics Observatory, launched in 2010, provides stunning high-resolution images of the sun in multiple wavelengths. SDO captures an image of the sun every 12 seconds, creating detailed movies of solar activity. These observations have revealed the complex dynamics of the solar atmosphere in unprecedented detail. The Parker Solar Probe, launched in 2018, is the closest spacecraft to the sun, diving through the outer corona to make direct measurements of the solar environment. Parker has already made groundbreaking discoveries about the structure of the solar wind and the behavior of the corona's magnetic field. By flying through the corona rather than just observing it from a distance, Parker is answering questions that eclipse observers have pondered for centuries. Despite these space-based capabilities, ground-based eclipse observations remain valuable. Total eclipses offer unique opportunities to study the innermost corona with high spatial resolution. The natural occultation provided by the moon is sharper and more complete than any artificial coronagraph can achieve. And eclipses provide opportunities for coordinated observations combining ground-based and space-based instruments. Modern eclipse expeditions are highly organized scientific endeavors. Teams of researchers travel to the path of totality with carefully planned observation programs. They bring specialized instruments designed to address specific scientific questions. High-speed cameras capture rapid changes in the corona during the few minutes of totality. Polarimeters measure the polarization of coronal light, revealing information about the corona's magnetic field. Spectrographs analyze the corona's composition and temperature. Amateur astronomers also make important contributions to eclipse science. With modern digital cameras and computerized telescopes, skilled amateurs can capture images rivaling those of professional observatories. Citizen science projects coordinate observations from multiple locations along the eclipse path, providing data that no single observer could collect. The democratization of astronomical equipment has turned eclipse observation into a collaborative endeavor involving thousands of participants. The study of how eclipses affect Earth's environment has become an active research area. During a total solar eclipse, the sudden reduction in sunlight causes rapid changes in temperature, wind patterns, and atmospheric chemistry. These changes provide natural experiments for studying atmospheric processes. Temperature drops during totality can be significant, sometimes exceeding 10 degrees Celsius in a matter of minutes. This rapid cooling affects air pressure and wind patterns, sometimes producing measurable changes in local weather. Scientists have deployed networks of weather stations along eclipse paths to study these effects in detail. The ionosphere, the electrically charged upper atmosphere that reflects radio waves, responds dramatically to eclipses. The sudden reduction in solar radiation causes the ionosphere to change rapidly, affecting radio communications and GPS signals. By studying these changes, scientists learn about the ionosphere's response to varying solar inputs. Wildlife responses to eclipses have fascinated observers for centuries, and modern studies have documented these behaviours systematically. Many animals respond to the sudden darkness as if night were falling. Birds return to their roosts, crickets begin chirping, and nocturnal animals may become active. Other animals show confusion or distress at the unexpected change. These observations provide insights into how animals use light cues to regulate their behaviour. Plants also respond to eclipses, though more subtly than animals. Some flowers begin to close during totality, responding to the reduced light as they would to approaching evening. Studies of plant responses during eclipses contribute to understanding of how plants sense and respond to their light environment. The technology for predicting and mapping eclipses has reached remarkable precision. Modern eclipse predictions use detailed models of the moon's shape, accounting for mountains and valleys on the lunar limb that affect the exact timing and duration of totality. These predictions are accurate to within fractions of a second and can map the path of totality to within meters. Interactive maps and smartphone applications allow anyone to determine exactly when and where an eclipse will be visible from their location. These tools have made eclipse chasing more accessible than ever, enabling millions of people to position themselves in the path of totality. Eclipse photography has evolved from a specialized scientific technique to a popular pursuit accessible to anyone with a camera. Modern digital cameras can capture stunning images of the corona, Bailey's beads, and the diamond ring effect. High dynamic range techniques allow photographers to capture both the bright inner corona and the faint outer streamers in a single image. Time-lapse photography documents the entire progression of an eclipse in compelling visual sequences. Social media has transformed how eclipses are experienced and shared. During recent eclipses, millions of photographs and videos have been posted online within hours of totality. Live streams allow people around the world to watch eclipses in real time, even if clouds obscure their local view. The communal experience of an eclipse, once limited to those physically present, now extends globally through digital connections. Virtual reality and augmented reality technologies are creating new ways to experience eclipses. VR recreations allow people to experience totality from the comfort of their homes. AR applications overlay eclipse information onto the real sky, helping observers understand what they're seeing. These technologies are particularly valuable for education, allowing students to explore eclipse phenomena interactively. The scientific value of eclipses extends beyond solar physics. Eclipses have been used to test theories of gravity, as we saw with the 1919 confirmation of general relativity. They provide opportunities to search for hypothetical objects near the Sun, such as the planet Vulcan, that 19th century astronomers believed might explain anomalies in Mercury's orbit. Although Vulcan was never found because the anomalies were actually due to relativistic effects, eclipse searches ruled out its existence. Lunar eclipses, while less dramatic than solar eclipses, also provide scientific opportunities. The colour of the eclipsed moon reveals information about Earth's atmosphere. By studying how much light reaches the moon during totality and what colours are present, scientists can assess the clarity of Earth's atmosphere and detect the effects of volcanic eruptions or other sources of atmospheric particles. Observations of lunar eclipses from space provide a unique perspective on Earth's atmosphere. Spacecraft orbiting the Moon can observe Earth's atmosphere backlit by the Sun during a lunar eclipse, revealing details about atmospheric structure and composition. These observations complement studies of exoplanet atmospheres, where similar techniques are used to analyze the atmospheres of planets orbiting other stars. The future of eclipse science is bright, if you'll pardon the expression. New instruments and techniques continue to be developed, promising ever more detailed observations. Coordinated campaigns involving ground-based observers, aircraft and spacecraft will maximize the scientific return from future eclipses. And as our understanding of the Sun deepens, new questions emerge that eclipses are uniquely positioned to address. Chapter 11: Famous Eclipses of the 20th and 21st Centuries. Let your mind drift now as we journey through some of the most memorable eclipses of recent times. Each of these events brought millions of people together in shared wonder, advancing science while reminding us of our place in the cosmic order. The total solar eclipse of June 8, 1918, crossed the United States from Washington State to Florida, passing through Denver, Colorado, and other major cities. This was the last total eclipse to cross the continental United States from coast to coast until 2017, making it a significant event in American astronomical history. The 1918 eclipse occurred during the final months of World War I and coincided with the early stages of the devastating influenza pandemic that would kill millions worldwide. Despite these challenging circumstances, astronomers mounted expeditions to observe the eclipse, and thousands of Americans witnessed totality. The eclipse provided a brief respite from the troubles of the time, a reminder that celestial wonders continue regardless of human conflicts. The total solar eclipse of May 29, 1919, which we explored in detail earlier, was perhaps the most scientifically significant eclipse of the 20th century. Its confirmation of Einstein's general relativity changed physics forever and demonstrated the power of astronomical observations to test fundamental theories. The total solar eclipse of June 30, 1954, crossed northern Europe, including parts of Sweden, Norway, and the Soviet Union. This eclipse was notable for the extensive scientific observations made by expeditions from multiple countries. It was also one of the first eclipses to be widely photographed by amateur astronomers using newly affordable camera equipment. The total solar eclipse of February 15, 1961, crossed southern Europe, passing through France, Italy, and Yugoslavia before continuing across the Soviet Union. This eclipse was observed by large crowds in Europe and was extensively covered by television, bringing the experience of totality to millions who couldn't travel to the path. The total solar eclipse of July 20, 1963, crossed Alaska, Canada, and Maine. This eclipse was significant for the extensive scientific observations made from aircraft, which allowed observers to extend their time in the moon's shadow by flying along the eclipse path. These airborne observations pioneered techniques that would be refined in later eclipses. The total solar eclipse of March 7, 1970, crossed Mexico and the eastern United States, with totality visible from cities including Norfolk, Virginia, and Nantucket, Massachusetts. This eclipse drew enormous public interest and was observed by millions of Americans. It was extensively covered by television and helped spark a renewed interest in astronomy among the American public. The total solar eclipse of June 30, 1973, was remarkable for the use of the supersonic Concorde aircraft to extend totality. A prototype, Concorde flew along the eclipse path at over twice the speed of sound, keeping pace with the moon's shadow for 74 minutes. This was by far the longest totality ever observed, and the extended observation time allowed scientists to study slow changes in the corona that couldn't be detected during a normal eclipse. The Concorde Eclipse expedition was a triumph of international scientific cooperation involving researchers from France, Britain, and the United States. The aircraft carried 7 experiments studying various aspects of the Sun and corona. The success of this mission demonstrated the potential for aircraft-based eclipse observations, though the expense of supersonic flight has limited subsequent applications. The total solar eclipse of February 26, 1979, was the last total eclipse visible from the contiguous United States until 2017. The path of totality crossed the Pacific Northwest and Northern Great Plains, with cities including Portland, Oregon, and Winnipeg, Manitoba experiencing totality. This eclipse was widely observed and extensively covered by media, including a memorable live broadcast by ABC News. The total solar eclipse of July 11, 1991 was one of the longest eclipses of the 20th century, with totality lasting up to 6 minutes and 53 seconds. The path crossed Hawaii, Mexico, and Central America, passing directly over major astronomical observatories on Mauna Kea in Hawaii. Scientists took advantage of the long totality and excellent observing conditions to make detailed studies of the corona. The 1991 eclipse was also notable for the large number of tourists who travelled to Mexico to observe it. Eclipse tourism was becoming an increasingly significant phenomenon, with travel companies offering specialised eclipse trips. The economic impact of eclipse tourism would grow substantially in subsequent decades. The total solar eclipse of August 11, 1999, was the last total eclipse of the 20th century and one of the most widely observed in history. The path of totality crossed Central Europe, passing through major cities including Munich, Stuttgart, and Bucharest. An estimated 350 million people lived within the path of totality, and millions more travelled to witness the event. The 1999 eclipse generated enormous media coverage and public interest. It was the first eclipse of the internet age, with websites providing real-time updates and live video streams. Unfortunately, weather conditions were poor across much of the path, with clouds obscuring the view for many observers. Those who did see totality reported a profound and moving experience. The total solar eclipse of June 21, 2001 crossed southern Africa, with totality visible from Zambia, Zimbabwe, Mozambique, and Madagascar. This eclipse was notable for the large number of eclipse tourists who travelled to Africa, contributing significantly to local economies. The clear skies typical of the African dry season provided excellent viewing conditions for most observers. The total solar eclipse of December 4, 2002 crossed southern Africa and Australia. Totality was visible from parts of South Africa, Mozambique, and the Australian outback. This eclipse was significant for the scientific observations made from multiple locations and for the continued growth of eclipse tourism. The total solar eclipse of March 29, 2006 crossed Africa, Turkey, and Central Asia. The path of totality passed through Libya, Egypt, Turkey, and Kazakhstan, among other countries. This eclipse was widely observed and extensively studied, with scientific expeditions deployed along the entire path. The total solar eclipse of August 1, 2008 crossed northern Canada, Greenland, Russia, Mongolia, and China. This eclipse was notable for the large number of observers in China, where millions witnessed totality. The eclipse occurred just days before the opening of the Beijing Olympics, adding to the celebratory atmosphere. The total solar eclipse of July 22, 2009 was one of the longest eclipses of the 21st century, with totality lasting up to 6 minutes and 39 seconds. The path crossed India, Nepal, Bangladesh, Bhutan, Myanmar, and China before continuing across the Pacific Ocean. An estimated 2 billion people lived within a day's travel of the path of totality, making this potentially the most accessible eclipse in history. The 2009 eclipse was extensively observed despite challenging weather conditions in many areas. In India, the eclipse coincided with the monsoon season, and clouds obscured the view for many observers. Those who found clear skies, however, witnessed a spectacular event with an exceptionally long totality. The total solar eclipse of November 13, 2012, crossed northern Australia and the South Pacific. The path of totality passed through Cairns, Australia, drawing tens of thousands of eclipse tourists. Clear skies provided excellent viewing conditions, and the eclipse was extensively photographed and broadcast. The total solar eclipse of March 20, 2015, crossed the North Atlantic, with totality visible only from the Faroe Islands and Svalbard. This eclipse was challenging to observe due to the remote locations and unpredictable weather, but thousands of dedicated eclipse chasers made the journey. The eclipse was also visible as a deep partial eclipse across Europe, where millions observed it. The total solar eclipse of March 9, 2016, crossed Indonesia and the Pacific Ocean. Totality was visible from Sumatra, Borneo, Sulawesi, and other Indonesian islands. This eclipse drew large numbers of tourists to Indonesia and was extensively covered by international media. The total solar eclipse of August 21, 2017, was one of the most significant astronomical events in American history. For the first time since 1918, a total eclipse crossed the continental United States from coast to coast, with the path of totality stretching from Oregon to South Carolina. An estimated 215 million American adults watched the eclipse either directly or electronically, making it perhaps the most observed eclipse ever. The 2017 eclipse generated unprecedented public interest and media coverage. Millions of Americans traveled to the path of totality, causing traffic jams in rural areas that had never experienced such crowds. Hotels along the path were booked months in advance, and eclipse glasses sold out nationwide. The eclipse was a shared national experience, bringing together people of all backgrounds in appreciation of a celestial wonder. Scientific observations during the 2017 eclipse were extensive and coordinated. NASA sponsored numerous research projects, and citizen scientists contributed observations from thousands of locations. High-altitude balloons, aircraft, and ground-based instruments collected data on the corona, the ionosphere, and environmental responses to the eclipse. The 2017 eclipse also demonstrated the power of eclipses to inspire interest in science. Surveys found that millions of Americans developed a greater interest in astronomy after witnessing the eclipse. Science educators reported increased engagement from students. The eclipse served as a reminder that direct experience of natural phenomena can be profoundly motivating. The total solar eclipse of July 2, 2019, crossed Chile and Argentina, with totality visible from several major observatories in the Atacama Desert. The clear, dry conditions typical of this region provided excellent viewing, and the eclipse was extensively observed by professional and amateur astronomers. The total solar eclipse of December 14, 2020, again crossed Chile and Argentina, making South America a favoured destination for eclipse chasers. This eclipse occurred during the COVID-19 pandemic, which limited travel and gathering, but didn't diminish the wonder of those who witnessed totality. The annular solar eclipse of October 14, 2023, crossed the western United States, Central America, and South America. While not a total eclipse, This event drew significant public interest as a preview of the total eclipse that would follow in 2024. The total solar eclipse of April 8th, 2024 crossed Mexico, the United States, and Canada, with totality visible from Texas to Maine. This eclipse was eagerly anticipated after the success of the 2017 eclipse and drew millions of observers. The path of totality crossed several major cities, including Dallas, Indianapolis, Cleveland, and Buffalo, making it highly accessible. The 2024 eclipse occurred near solar maximum when the sun's activity cycle is at its peak. This meant that the corona displayed complex structures with numerous streamers and prominences. Observers reported that the corona was more impressive and dynamic than during the 2017 eclipse, which occurred closer to solar minimum. These recent eclipses have demonstrated the enduring power of celestial events to capture human attention and inspire wonder. Despite all our technology and scientific understanding, there remains something primal and profound about standing in the shadow of the moon and watching the sun disappear. Each eclipse is unique, shaped by the sun's activity, the weather, the location, and the personal circumstances of each observer. Chapter 12. The Future of Eclipses and Our Cosmic Perspective. As we approach the end of our journey together, let us turn our gaze toward the future. What eclipses await us in the coming years and decades? And what do eclipses teach us about our place in the universe and the preciousness of our cosmic situation? The next few decades will bring numerous opportunities to witness eclipses. Let me guide you through some of the notable events that await patient observers. The total solar eclipse of August 12, 2026 will cross the Arctic, Greenland, Iceland and Spain. Totality will be visible from major cities including Reykjavik and Valencia, making this eclipse relatively accessible for European observers. The maximum duration of totality will be about 2 minutes and 18 seconds. The total solar eclipse of August 2nd, 2027 will cross North Africa and the Middle East, with totality visible from Morocco, Algeria, Tunisia, Libya, Egypt, Saudi Arabia, and Yemen. This eclipse will have a long totality of up to 6 minutes and 23 seconds, making it highly attractive for eclipse chasers. The path will cross several ancient sites, including Luxor in Egypt, adding historical resonance to the astronomical event. The total solar eclipse of July 22, 2028 will cross Australia and New Zealand, with totality visible from Sydney, one of the few major world cities to experience totality in the coming decades. This eclipse will draw enormous crowds to Australia and will be extensively covered by media worldwide. The total solar eclipse of November 25, 2030 will cross southern Africa and Australia, with totality visible from Namibia, Botswana, South Africa, and the Australian outback. This eclipse will offer excellent viewing conditions in the clear skies of these regions. The total solar eclipse of March 30th, 2033 will cross Alaska and will be one of the few total eclipses visible from the United States in the 2030s. The path of totality will cross remote areas, making observation challenging but rewarding for those who make the journey. The total solar eclipse of September 2nd, 2035 will cross China, Korea, and Japan, with totality visible from major cities, including Beijing and Tokyo. This eclipse will be witnessed by hundreds of millions of people and will generate enormous public interest in East Asia. The total solar eclipse of August 21st, 2036 will cross the Mediterranean and Middle East, with totality visible from Spain, the Balearic Islands, Sardinia, Turkey, and Iran. This eclipse will occur exactly 19 years after the 2017 American eclipse, completing one Saros cycle. Looking further ahead, the total solar eclipse of April 20th, 2042 will cross Southeast Asia, with totality visible from Indonesia, Malaysia, and the Philippines. The total solar eclipse of April 9th, 2043 will cross Russia, Japan, and the western United States, with totality visible from parts of California and Oregon. The total solar eclipse of August 23rd, 2044 will cross Canada and the northern United States, with totality visible from Montana and North Dakota. The total solar eclipse of August 12th, 2045 will cross the United States from California to Florida, offering Americans another coast-to-coast eclipse experience. These future eclipses remind us that the celestial clockwork continues to turn, bringing regular opportunities for wonder and discovery. Each eclipse is a gift from the cosmos, a chance to witness the precise alignment of Sun, Moon, and Earth that creates these remarkable events. But eclipses also remind us that we live in a special time in Earth's history. The near-perfect match between the apparent sizes of the Sun and Moon, which makes total solar eclipses so spectacular, is a temporary coincidence. The Moon is slowly moving away from Earth, receding at a rate of about 3.8 centimeters per year. This may seem insignificant, but over millions of years, it adds up. About 600 million years ago, the Moon was closer to Earth and appeared larger in the sky. Total solar eclipses were more common and lasted longer. The Moon would have covered the Sun completely with room to spare, hiding the inner corona that we find so beautiful during modern eclipses. In about 600 million years, the Moon will have moved far enough away that it will no longer be able to completely cover the Sun. All solar eclipses will be annular, with a ring of sunlight always visible around the Moon's silhouette. The total solar eclipses that we treasure will be impossible. Future inhabitants of Earth, if there are any, will never see the corona revealed in all its glory during totality. We live in the sweet spot, the cosmic moment when the Moon is just the right distance from Earth to create total solar eclipses. This is not a coincidence that was arranged for our benefit. It's simply the way things happen to be right now. But it does make our total eclipses precious, fleeting gifts that won't last forever on the cosmic timescale. This perspective invites a certain humility and gratitude. We are small creatures on a small planet, orbiting an ordinary star in an ordinary galaxy. Yet we have the privilege of witnessing one of the most beautiful phenomena in the solar system, a phenomenon that requires the precise alignment of three celestial bodies and the fortunate coincidence of their apparent sizes. Eclipses also connect us to all of humanity, past, present, and future. When we watch an eclipse, we participate in an experience shared by countless generations before us. The ancient Babylonians who first recorded eclipses on clay tablets, the Chinese astronomers who predicted them for emperors, the Greek philosophers who puzzled over their causes, the medieval Europeans who feared them as omens, the modern scientists who used them to probe the sun's secrets. All of these people looked up at the same sun and moon that we see, watched the same shadows cross the sky, felt the same mixture of awe and wonder, and future generations will continue this tradition, standing in the moon's shadow on days we will never see, perhaps on worlds we haven't yet imagined. Eclipses are threads connecting us across time, reminders that we are part of a continuous human story of observation, wonder, and understanding. The scientific study of eclipses has taught us profound truths about the universe. From eclipses, we learned that Earth is round. We learned the distance to the moon and sun. We learned that light bends in the presence of gravity, confirming Einstein's revolutionary theory. We learned about the sun's corona, its composition, its temperature, its role in producing the solar wind that fills our solar system. But perhaps the deepest lesson of eclipses is not any specific scientific fact. It's the reminder that we live in a comprehensible universe, a cosmos governed by laws that human minds can discover and understand. The same mathematics that describes the fall of an apple describes the orbit of the moon. The same physics that governs light in a laboratory governs starlight's bending around the sun. The universe is not arbitrary or chaotic. It follows patterns that we can discern through careful observation and creative thinking. This comprehensibility is itself a source of wonder. Why should the universe be understandable? Why should beings evolved on one small planet be able to grasp the laws governing the entire cosmos? These questions touch on deep mysteries that science alone cannot answer. But eclipses remind us that understanding is possible, that the universe reveals its secrets to those who watch carefully and think deeply. As you rest now, perhaps drifting towards sleep, carry with you the images and ideas we've explored together. The ancient astronomers watching the sky from Babylon and Beijing, the shadow of the moon racing across Earth's surface, the ghostly corona revealed during totality, Einstein's equations describing the bending of starlight, the long chain of observers stretching back through history and forward into the future. Eclipses are invitations to look up, to remember that we live on a planet in space, to feel our connection to the cosmos. They are moments when the ordinary business of life pauses, and we are reminded of larger realities. The sun that rises each morning and sets each evening is a star, a nuclear furnace converting hydrogen to helium and radiating energy into space. The moon that waxes and wanes each month is a world, a sphere of rock that has accompanied Earth for billions of years. And we are the observers, the conscious beings who can appreciate these wonders and seek to understand them. Chapter 13. Closing Reflection and Call to Action. As our journey through the story of eclipses comes to a close, let yourself sink into the peace of this moment. We have travelled far together, from the myths of ancient civilizations to the cutting edge of modern science, from the terror of our ancestors at the darkening sun to the wonder of eclipse chasers standing in the moon's shadow. Eclipses remind us that we are part of something vast and ancient. The dance of sun, moon and earth has been continuing for billions of years, long before any human eye watched the sky. It will continue for billions of years more, long after we are gone. We are brief visitors to this cosmic show, privileged to witness a few eclipses during our short lives. But what witnesses we are! We have learned to predict eclipses centuries in advance, to travel the world, to stand in the moon's shadow, to use these moments of darkness to illuminate the deepest truths of physics. We have transformed fear into understanding, superstition into science, without losing the capacity for wonder that makes eclipses so meaningful. If you have never seen a total solar eclipse, I encourage you to make the journey. No photograph, no video, no description can capture the experience of standing beneath a darkened sky in the middle of the day, watching the corona bloom around the black disk of the moon, feeling the temperature drop and the world grow still. It is one of the most profound experiences available to human beings, a moment when the abstract knowledge that we live on a planet in space becomes visceral and immediate. The coming years will bring many opportunities to witness totality. Perhaps you will travel to Spain in 2026, or to Egypt in 2027, or to Australia in 2028. Perhaps you will wait for an eclipse to come to you, patient as the ancient astronomers who watched and recorded and waited. Whenever and wherever you experience your first totality, you will join a community stretching back thousands of years, all of us united by the simple act of looking up. And if you have already seen a total eclipse, you know the longing to see another. Eclipse chasers speak of the addiction, the irresistible pull that draws them across oceans and continents to stand once more in the moon's shadow. Each eclipse is different, shaped by the sun's activity, the weather, the landscape, the company. Each totality is a unique and unrepeatable moment, a gift that can never be exactly replicated. Lunar eclipses, too, deserve your attention. They lack the drama of total solar eclipses, but they have their own quiet beauty. The slow progression of Earth's shadow across the moon, the deepening red of totality, the gradual return of normal moonlight, all of this unfolds over hours, inviting contemplation and reflection. You can watch a lunar eclipse from your backyard, sharing the experience with friends and family, needing nothing more than clear skies and patience. Whether solar or lunar, eclipses connect us to the cosmos in ways that few other experiences can match. They remind us that we are not separate from the universe, but embedded within it, participants in the great dance of celestial bodies that has been continuing since the solar system formed 4.5 billion years ago. As you drift towards sleep now, carry with you the wonder of eclipses. Remember the ancient observers who first noticed patterns in these events and began the long journey toward understanding. Remember the scientists who used eclipses to measure the cosmos and test the deepest theories of physics. Remember that you, too, are part of this story, a conscious being capable of appreciating the beauty and order of the universe. The shadows will continue to fall, the sun and moon will continue their eternal dance, and there will always be those who look up in wonder. May you be among them. Thank you so much for spending this time with me tonight. If you enjoyed this gentle exploration of eclipses, I would be so grateful if you would take a moment to like this video and subscribe to the channel. Your support helps me create more content like this, more opportunities for us to explore the wonders of the universe together in this peaceful, relaxed way. If you're still awake, you might enjoy some of my other videos, where we explore different corners of the cosmos with the same gentle curiosity. And if you're drifting off to sleep, I wish you peaceful dreams, filled with stars and shadows, with the soft glow of the corona and the ruddy light of the eclipsed moon. Until next time, rest well, dream deeply, and remember to look up at the sky whenever you can. The universe is always there, waiting to fill you with wonder. Good night, dear friend, and thank you for joining me on this journey through the shadows.